So this is ELC 131, Circuit Analysis 1. The topic of this presentation is the analysis of a series circuit. Now we see an example of a simple series circuit on the board. A source voltage of 12 volts, 3 resistors connected in series, R1 10 ohms, R2 20 ohms, and R3 30 ohms. Now, when we provide a path for current for IS or for VS, then VS will supply some current that we refer to as IS or I total. And Kirchhoff's current law tells us that the current leaving the source has to flow through R1, it has to flow through R2, and it has to flow through R3. So our first equation for the analysis of this circuit states that I source equals IR1 equals IR2 equals IR3 equals ... symbolizing that regardless of how many resistors we connect in series, those currents will be the same. Now, whenever current flows through a resistive element, there'll be a voltage drop, a potential difference across those resistances. And again, the algebraic signs associated to these voltage drops are determined by the direction the current flows through these. And Kirchhoff's voltage law tells us that in this circuit, the sum of the individual voltage drops must add up to the voltage source. So we can say that V source, also named or termed V total, equals VR1 plus VR2 plus VR3 plus ... again symbolizing that regardless of how many resistors we connect in series, the sum of their voltage drops will add up to the source voltage or total voltage applied to this series combination. Now the third equation is really derived through using these two equations and Ohm's law. And this equation states that the total resistance seen by the voltage source, Vs, is equal to the sum of the individual resistors. So RT equals R1 plus R2 plus R3 plus ... again symbolizing that regardless of how many resistances we connect in series, the sum of their individual resistances will add up to be the total resistance of the circuit. And the third equation, again, is just a combination of these two equations and says that the total power delivered by the source is equal to the individual power dissipations in each resistor. So if we combine the power dissipated in R1, the power dissipated in R2, the power dissipated in R3, this adds up to be the source power or the total power in the system. So let's analyze this circuit. Our analysis steps always start with finding the total resistance of the circuit. And I want you to always follow these steps in that you want to write down the equation first. After we express RT, we're going to substitute in our known values for R1, R2, and R3, and then solve for, in this case, a total resistance of 60 ohms. Now, this is kind of important because understand that this 12 volt source, Vs, simply cannot tell the difference between the original circuit and this circuit with one single resistance. The source can't tell the difference. In either case, it's going to deliver the same amount of current. So the next step is to find the source current, or the total current, which is just Ohm's law. I total equals V source divided by R total. 12 volts divided by 60 ohms gives us 200 milliamps. Now, we always want to express our quantities using correct engineering notation and preferred SI prefixes. So we express this as 200 milliamps and not 0.2 amps. Now that we have found the source current, 200 milliamps, we can determine or calculate the individual voltage drops. So VR1 equals I times R1, again, Ohm's law, 200 milliamps times 10 ohms gives us 2 volts. VR2 equals I times R2, 200 milliamps times 20 ohms gives us 4 volts, and VR3 gives us, or is I times R3, 200 milliamps times 30 ohms gives us 6 volts. Now we'll go back and do a quick check to make sure that we haven't made some blunder. And 2 volts plus 4 volts plus 6 volts indeed add up to 12 volts. So we know that this equation is true. Now we can calculate the power consumed in each resistor, again using our power formula, where PR1 equals VR1 times I, 2 volts times 200 milliamps gives us 400 milliwatts. PR2 equals VR2 times I, 4 volts times 200 milliamps is 800 milliwatts, and PR3 equals VR3 times I, 6 volts times 200 milliamps is 1.2 watts. Now, the total power delivered by the source can be calculated 2 ways. We can find the sum of the individual power dissipations, or we can use our power formula to say that the source power, or the total power, equals V source times I, 12 volts times 200 milliamps is how much? 2.4 watts. And if we add these individual power dissipations up, we'll also get 2.4 watts. So this is the steps to follow in order to analyze this series circuit to find R total, the source current, the individual voltage drops, and the individual power dissipations. Now, there's oftentimes when analyzing a series circuit, when we want to find the voltage drop across the resistor, yet we don't need to find the current. So we'll make use of an expression or an equation that I call the voltage divider equation. Now, some textbooks refer to this as the voltage divider rule or the voltage divider formula, but the general format expression is that VRX equals V source times RX over R total, where X can be any resistor, R1, R2, or R3. So for example, let's use this voltage divider equation to find the voltage across resistor R2. So our equation would be VR2 equals V source times R2 over R total. And we'll substitute in our known values, 12 volts times 20 ohms over 60 ohms, giving us, of course, 4 volts. Now, this is really nothing magical here because VR2 equals I times R2, and I equals VS over R total. So all we've done with this voltage divider formula is we have put the R's together inside the parentheses and taken V source out of the parentheses. But I'll make use of the voltage divider rule, the voltage divider formula, the voltage divider equation quite often because there's, again, many times that I'm not concerned with the current in the circuit and all I want to find is the voltage drop across an individual component.